With my electric boat and powered paddleboard projects last summer, I had so much fun testing different propeller designs, and it would be selfish of me not to share that fun with you, so I'm going to be holding a boat propeller design competition. My viewers will be able to submit their own propeller designs, and I'll pick a bunch of them to test on my autonomous boat. I'll be measuring the efficiency, so the most efficient propeller wins. The prizes are store credit to PCBWay. The first place winner gets $300, the second place winner gets $200, and the third place winner gets $100 in store credit. If you're not a PCB designer, then don't worry, because you can also spend the credit on their 3D printing or CNC machining services. To test all the different propellers, I'm going to be using my dear old catamaran here that has already been repurposed several different times for several different projects. Its previous mission was being a test bed for different abnormal forms of propulsion, so we're going to need to make a few modifications before it'll work as a propeller test platform. I designed some motor mount parts and printed them on the Prusa XL. This is one of the first projects I've ever used dual extruders for, and it's such a game changer. The red support material is PLA, and the yellow structural material is PETG. The cool part is that these two materials don't stick together at all, which makes removing the support material super easy. For this project, I'm going to be using this 5064 200 kV waterproof motor. It gets screwed onto the motor mount using some M3 screws, and then the motor mount gets attached to a 5/8 inch square wooden dowel. A hydrodynamic nose cone gets attached to the front of the motor mount, and a streamlined trailing edge goes on behind the wooden dowel. That just glues in place with Gorilla Glue. The whole motor assembly attaches onto a pivoting mount on the front of the boat. It pivots so that I can easily pull the motor up out of the water and swap propellers. Next, it was time to make some preliminary test propellers, and for this, I'm using the 3-profile on-shape propeller template from Holbrook Aerospace. This template allows you to create a fully parametric propeller where everything can be adjusted by editing numbers instead of editing the model itself. The main parameters I'm going to be playing with in this video are the tip diameter and pitch. Here you can see that if we change the tip diameter, it changes the length of the blades. Here I changed it to 200 millimeters, and now I'm going to change it back to 120 millimeters. The 3 angle values over here control the angle of incidence at the root of the blade, the middle of the blade, and the tip of the blade. So let's say we want the pitch of the blade to be much lower. We just adjust the numbers, and there you go. Now it has a super low pitch like a trolling motor prop. Thanks to Holbrook Aerospace for making this Onshape model free for everyone to play with. It's available at the link in the description. Onshape is free for hobbyists, so all you have to do is sign up for an account and then you can make a copy of the propeller model and start playing with it. That will give everyone entering the propeller design competition a good starting point for roughly the size and shape they should aim for. For more detailed instructions on how to use this template, check out this video from Holbrook Aerospace. There will also be a link in the description to that. I'm going to be using this CAD model to generate a bunch of different sizes of props, and these will help me narrow in on the optimal diameter and pitch for this motor. For all these preliminary tests, I'm going to be FDM printing the propellers on the Prusa XL. And again, I'm using the dual extruders for support material, which makes printing the overhanging blades super easy. As with any FDM printer, the surface finish isn't perfect, but at least it'll help me iterate quickly and hopefully narrow in on the optimal propeller size for this motor. For the actual competition propellers, I'll be resin printing them, so they should have a near perfect surface finish. And then it was off to the lake for a test drive with the new propulsion system. The first thing I noticed is that this motor has some power. The second thing I noticed is that the motor mast is ventilating a lot. It's not nearly hydrodynamic enough, so we'll need to fix that later. On this day, I tested 3 different propellers, 120mm, 130mm, and 140mm. All 3 had the same blade pitch. I ran the same waypoint mission for each prop at a consistent 1.5 meters per second, and used MavExplorer to generate these watt-hour per kilometer graphs. Here are the results. The smallest propeller was the most efficient, so that's good to know. The next day I printed 3 more propellers. These were 110mm, 100mm, and 90mm in diameter. I also printed a streamlined leading edge for the motor mast and glued that into place, and then it was back to the lake to test these smaller propellers. And I also printed a 120mm prop with a thinner cord length just to test out for fun. Upon throttling up the boat, it was clear that the new streamlined motor mast worked really well. You can see that the flow stays attached all the way down to the motor, so there's no ventilating going on, so that's great. Here are the test results. It turned out that 120mm is the optimal size. Any smaller than that and the efficiency starts to get worse pretty quick. And the 120mm thin cord version took the cake, beating the regular version ever so slightly. So now that we know that 120mm is roughly the optimal size, it's time to start playing with different pitch angles. I also made a new rudder, because the first one had the pivot point at like 45% of the cord, which is probably behind the center of pressure, so it would start to wiggle at higher speeds. The new one has its pivot point at like 33% of the cord, and that was much more stable. So here are the results for a bunch of different pitch variants. I'm going to start adding the pitch numbers in here. The first number is the pitch at the root, the second number is the blade pitch in the middle, and the third number is the pitch at the tip of the blade. And it turns out that all the propellers in my previous tests had pitch angles that were way too low. The highest pitch propeller was over 2 times as efficient as the lower pitch angles that I started out with. It's pretty incredible how much of a difference a few degrees makes. It's worth noting here that the optimal pitch angle is entirely dependent on the speed of the boat, so if I were testing at a much lower speed, the lower pitch propeller would almost definitely be more efficient. The next day I printed a bunch more props with even steeper pitch angles to try. I also started playing with the twist angle a bit, giving some props a steeper angle at the root and a shallower angle at the tip, and others vice versa. Here's the boat running waypoint mission after waypoint mission, and I was swapping out the props on each lap. I also started programming 2 speeds into each test. The boat does 1 lap at 1.5 meters per second and then a second lap at 2 meters per second. That way we can start to get a feel for how different pitch angles affect efficiency at different speeds. And sure enough, the higher pitch props do better at 2 meters per second, but I also found the limit for pitch angle. This prop here had the highest pitch angle, but it performed a little worse than this one here, that had a slightly lower pitch angle. I also tested slightly smaller and larger props with higher pitch angles, but it seems that 120 millimeters is still roughly the optimal diameter here. The next day I printed more twist variants, some with a ton of twist like this one, and others with a flatter blade profile like this one. So then I headed back to the lake and ran all these props on the boat, and this is the result. Pretty much all of them did quite well except for the one prop with a super low angle of attack at the tip. It performed the worst. So at this point I had tested quite a few propellers, and had more or less figured out the recipe for what works decently well. Knowing the optimal size and pitch of propellers for this motor is super important, because the size and pitch makes such a huge difference in the propeller's performance. Like the size of the blade is probably even more important than the blade design itself. You could take the best propeller design in the world, and even if it's just like 10 millimeters too big or too small for this motor, it might perform terribly. And to complicate things even further, the optimal size of propeller for this motor is dependent on the blade design and pitch. So as an example, these prop blades have a very low aspect ratio, or in other words, they're short and fat. But if they had a higher aspect ratio and were more long and narrow, like an airplane propeller, then the optimal size would likely be larger than it is now. So there are just so many codependent factors that have to be considered. This is why professional propeller designers use a lot of CFD simulations and iterative design tools to narrow in on the optimal geometry. Now I know most of you out there don't have access to these super advanced tools, and that's why it was very important for me to print out all these test props. I'm hoping this will at least give people a good starting point for their own designs. All these different props are saved as versions in the Onshape model, and this 120mm plus 15 plus 20 plus 25 version is probably your best bet for a starting point. Oh, by the way, I'll be at OpenSauce again this year. This is Big Willie, and he told me to tell you that there are 500 exhibitor booths that need to be filled. So if you want to show off your project and get into OpenSauce for free, definitely think about exhibiting. Last year, the event was a ton of fun, and I'm super excited to be there again this year. It's in San Francisco on June 15th and 16th. Go check it out.
Toroidal propellers are going to swoop in from the heavens and save us all.
Now to answer all the inevitable comments that will say, why don't you just test the propellers in a bucket or a pool? It's because then we would be measuring static thrust. Having a propeller optimized for static thrust is only really useful if you're building a tugboat or a trolling motor, something that doesn't go very fast. I'm hoping these propeller designs will be used for boats and hydrofoil projects in the future, so that's why I want to test them at speed. Now let's talk about the actual competition itself. My plan is to run each propeller through a waypoint mission where the speed of the boat is slowly increased until it simply can't go any faster. So the data for each prop should look something like this. We're going to be ranking the props by their efficiency. The efficiency will be measured in grams of thrust per watt, and we'll be taking measurements starting at 2 meters per second all the way up to whatever the max speed is for the given propeller. The propeller with the most area under the curve wins. The math people tell me that this is called the integral. So there's basically 2 ways to score a good integral efficiency measurement in this competition. The first is to make a prop that's really efficient, because that obviously gives you more area under the curve. The second way is to design a prop with a higher max speed, because this will extend the curve to the right, which also leads to more area under it. For all my previous prop testing videos, I was measuring watt-hours per kilometer. This time around, I decided to measure grams of thrust per watt because it should reduce the influence from the wind. I'm going to try and run these tests with as little wind as possible, but if there is any, it shouldn't have as much of an effect on the actual efficiency measurement itself. Instead, it'll mostly just affect the position of the data relative to the x-axis, which is speed. This also matters, but it's not quite as significant as the y-axis. So here's what our prop test waypoint mission looks like. It took way longer than it should have for me to arrive at a system that works. At first I thought a square waypoint mission would work, and that would have been really convenient because the boat really never gets that far away, but it turned out that the turns were making the data look pretty bumpy, like this. Next I tried putting an Arduino in series with the throttle signal. It would basically check to see if the data logger was logging, and if it was, then it would ignore the throttle command coming from the ArduPilot, and instead just send its own throttle command to the ESC that would have the motor start at 20% and slowly ramp up to 100%. That would have in theory given us a nice smooth efficiency curve. The issue here is that it turned out that the ArduPilot really didn't like having its throttle control signal hijacked. The steering controller would freak out and steer the boat far away from its next waypoint, so I scrapped that idea. Next I just painstakingly made a waypoint mission by hand with a crapload of waypoints, and at each waypoint there was a do change speed command that would increase the speed by 0.1 meters per second. I went to go test that, but it turned out that if the waypoints were too close together, ArduPilot would ignore the speed change command. So I had to space the waypoints further apart, which makes testing each prop take longer than it could, but oh well, at least our data is looking nice and smooth now. At the beginning and end of the test runs, there are do set servo commands. That's how the flight controller tells the data logger to start and stop logging. So the whole thing is pretty automated. All I have to do is flip a switch and the boat goes and does its thing. On the topic of speed, I initially wanted to test the props from 0 meters per second up to as fast as they'd be able to push the boat. But it turns out that's easier said than done, because the current sensor I'm using is really non-linear at lower current values. For this boat to go like 1 meter per second, it only uses a fraction of an amp, and with the hardware I have now, that's really not possible to measure accurately. So that's why I'm starting at 2 meters per second. For the better performing props I've tested so far, the boat has gotten up to just shy of 3.5 meters per second. I'm hoping someone will be able to create a design that gets us up closer to 4 meters per second. That would be really impressive. Now let's talk about the motor driver. I'm using this old Vesk here, and it's in speed control mode. This means the throttle level is proportional to the RPM of the motor. However, there's a 400 watt maximum power limit programmed into the Vesk. This will effectively limit the max RPM of the motor before it reaches full throttle. I mapped the RPM at full throttle to around 3000. I chose this number because that was the RPM that these lower pitch props I tested earlier were getting up to. They performed really poorly, so I'm sure that any prop that spins this fast will have no chance of winning the efficiency competition. These lower pitched props were basically the equivalent of a car trying to drag race in first gear the entire time. The motor is making power, but it just isn't being utilized effectively. At 400 watts, the better performing props I've tested are getting up to a little over 1700 RPM. So setting the max potential RPM of the motor to 3000 should give us enough headroom just in case there's some spooky prop design that can somehow make a lot of thrust with higher RPM and lower torque. Because remember, we have a 400 watt limit, and amps times volts equals watts. Amps and volts are equivalent to torque and RPM. So at our 400 watt limit, we can either have more RPM and less torque, or more torque and less RPM. The ratio can be whatever, it's just going to always balance out to 400 watts. Unless, of course, you have a prop that has so little rotational resistance that the RPM maxes out and it's still not even pulling enough current to hit 400 watts. But that's unlikely. Speaking of current, the max phase amps is set to 37.5. I've never really seen any prop exceed 32 phase amps, and that was even during a static test where the boat was pushing into the dock, so I don't think we'll ever hit the limit of 37.5 amps. So why use a 400 watt max power limit in the first place? There are 3 main reasons. First, it's just more fair if each prop is tested up to the exact same power level. Without the 400 watt cap, the variance in rotational resistance of all the propellers would lead to different props spinning at different RPMs, which would make them all pull different amounts of power, which would make the competition weird. The second reason for capping the max power is that even at just 500 watts, these displacement hulls are basically up on plane, and the motor comes up out of the water high enough for the propeller to start ventilating, which is no good. The third reason is that by artificially capping the power, we're running the motor at a lower duty cycle, like around 60%. Because of this, the battery voltage doesn't matter as much, and I don't have to run each test at the exact same battery voltage. That would be inconvenient. The duty cycle will just get a little higher as the battery voltage drops, since we're controlling for power, not RPM. During testing, I put my laptop on the boat to record the Vesk telemetry data. This is when I realized that 500 watts is way too fast to be driving with a laptop on the boat. It got up to around 3.6 meters per second, which is still only 61% duty cycle, so we could get a lot more power out of this motor if we wanted, but that would probably rip this boat apart. The max RPM we got up to here is 1900. Here's what a more reasonable 300 watt limit looks like. We're seeing 29 phase amps and 1700 RPM. This is with my best performing FDM printed propeller, by the way. If you want to know the mechanical torque of this motor, I think it's around 1.3 Newton meters, but that's just estimated based off the phase current and kV, so I'm not actually sure how accurate it is. Not only is PCBWay sponsoring the prizes for this contest, but they're also sponsoring this video. PCBWay is a full-feature custom PCB prototyping service. I've been using them a lot recently for a bunch of upcoming projects. Not only do they make the PCBs, but they can also source all of the components and assemble the PCBA. I just got these aluminum heat sinks machined by PCBWay, and they look great. Thanks again to PCBWay for sponsoring this video and all the prizes. Now back to testing. If anyone wants a free boat, found one. It's here, just come get it. To help the motor stay underwater at higher speeds, I added some little hydrofoil trim tabs to the back of the hulls. These lift the back of the boat up a bit, which helps keep the nose down. Without these, the motor would be pretty close to coming out of the water at 400 watts. So in order to record the data for this competition, I got some help from Mitch here, who is a software engineer from the area. He designed this ESP32 based data logger that measures current, voltage, GPS speed, and thrust with a load cell. The motor is mounted to this big pivoting arm that pushes down on the load cell. We calibrated it by having the boat pull on a string wrapped around a kitchen scale. That ended up working pretty well. To measure the current, we started off with this Hall effect sensor, and the data was so noisy. So then I switched over to a shunt resistor current sensor. This is your average ArduPilot power module, and it outputs an analog voltage signal that's proportional to the measured current. But the problem was that the ESP32's analog pins couldn't read the voltage signal all the way down to 0. It wouldn't read lower than 100 millivolts or so. My solution to this was maybe a little overkill. Instead of reading the current measurement with the ESP32, we're now reading it with the Pixhawk 4 flight controller, and the ESP32 is now reading the Mavlink messages from the flight controller. And those messages also contain battery voltage and GPS speed data, so we might as well just grab those while we're at it. Big thanks to Sebastian for helping me out with this. Sebastian, you're like a T-Rex. Sebastian dislocated his shoulder yesterday.
Yeah, I did.
So sad. So now the only thing the ESP32 is actually measuring is the thrust from the load cell, and then it writes all the data to the SD card. Despite all these changes, the current measurement is still not great. It's super non-linear at low current levels, so that's why I'm starting the prop testing out at 2 meters per second. That will keep our power measurements much more accurate. This is a toroidal propeller designed by Heinrich from Friendship Systems. They are the company who makes the online B-series propeller generator that I've used in several of my previous videos. Heinrich designed this prop with their CAD software called Cases. This CAD software is designed specifically to be used with shape optimization tools for iterative design and CFD type stuff. This software is ideal for creating CAD models of boat hulls, impellers, or really anything related to fluid mechanics that you intend to run through a simulation software. This is also the first SLA printed prop that I tested on this boat. I printed it on the Formlabs Form 3 Plus, and this is most likely the printer that I'll be using to print all the other props for this competition. And Formlabs wants me to tell you that they're hiring, so if you want to work for one of the best 3D printer companies out there, check out the link in the description. I did a quick preliminary test of this toroidal prop versus my best performing standard prop, and it actually won. The toroidal prop was 6% more efficient. Neither of these props have been optimized with CFD, so based on these results alone, we can't really conclusively say if toroidal propellers are indeed superior. But this is the first time I've ever had a toroidal prop outperform a standard prop, so that's exciting. So now onto the competition rules. The first rule is that you're only allowed to submit a propeller if you promise to not be sad if I don't test it. I'm going to test as many as I can, but I'll probably only be able to do around 20 propellers, and there might end up being a lot more submissions than that. I don't really know what to expect, but I probably won't be able to print and test all of them. I'm more likely to pick propellers that I think have a good chance of winning, or are just interesting.
I cannot figure out why the water just turned brown right there. It's not the light, it's not the sun hitting it in a weird spot. It's something else. There must be like a strong undercurrent right there all of a sudden. It's stirring up mud or something like that. It's super weird, I'm not sure.
Next rule. All the propellers have to use this hub, so that I can easily attach them to my motor. If you're using Onshape, then you can just copy this model and start adding your blades. Or, if you're using a different CAD program, you can just download the step file from Onshape. You should really try to use this model instead of just redrawing it so that the dimensions are exact and it fits on my prop adapter without any issues. The light blue part is the motor, the gray part is the prop adapter, and the dark blue part is the hub that you should add your blades onto. If you really need to, you can extend it out a bit like this, but otherwise it's probably best to keep it unchanged. The props have to spin clockwise if you're looking at it from the front, and if you're looking at it from the back, they should spin counterclockwise. To save resin, I have the inside hollowed out, and for printability reasons, there needs to be a small hole in the back. The next rule is just general printability. The trailing edge really shouldn't be any thinner than 0.6 millimeters. In this Holbrook Aerospace propeller template, you can change the trailing edge thickness with these parameters here, which is really cool. Here, I parametrically increased it to 1.5 millimeters, and boom, just like that. Suddenly, it's a thicker trailing edge. You can also make round trailing edges if you want, but if that's the case, it should still have a diameter of 0.6 millimeters or larger. The blade profile needs to be thick enough not to break during the test. With these test props, the airfoil profile was 5 millimeters thick at the root of the blade and 4 millimeters thick at the middle of the blade, and around 2.5 millimeters thick towards the tip. It's probably smart not to have anything thinner unless you have something like a toroidal propeller that is supported on two sides. Also, the blades can't cover up this hole that runs all the way through the hub because that's where the screw goes in that secures the propeller in place. Size-wise, it needs to fit on the build platform of the Formlabs Form 3 Plus, which is 145 by 145 millimeters. If you submit a propeller, I'll check it out, and if I think it's not printable, then it's not going to get accepted, so be mindful of that. Timeline-wise, I don't know exactly when the deadline for submissions will be, probably around a month from when this video is posted, but I'll post the exact date on my website, and a link to that can be found in the video description. After having already tested these baseline propellers on my boat, Wouter from AirShaper offered to run a simulation on the design. The results were pretty interesting. We found that the tip vortices could be reduced, the upper surface of the blade might benefit from more camber, and the point at the back of the propeller is not quite gradual enough because there's some flow separation happening there. I'll put a link to our full conversation in the video description. That's all for this video. I'm looking forward to seeing people's propeller designs, and if you have any questions, feel free to contact me through my website. Thanks for watching. Bye.